When dealing with dryer circuits, it's essential to understand the grounding requirements outlined in the National Electrical Code, or NEC. Specifically, Section 250.140 addresses the grounding of equipment connected by cord and plug. The situation you've described involves an existing 3-wire dryer circuit that was initially fed from the service equipment, but now originates from a subpanel due to a service upgrade. In this scenario, the original service equipment effectively becomes a subpanel because of the new meter section incorporating a main breaker. According to NEC Section 250.140, there are specific conditions that must be met to allow the continued use of a 3-wire circuit for supplying appliances like dryers. One critical requirement is that the circuit must originate from the service equipment. Since the dryer circuit is now supplied by a subpanel and not the service equipment, it no longer meets this requirement. The NEC emphasizes safety, especially when dealing with appliances like clothes dryers where a ground fault could pose a significant hazard to people. Section 250.141 stipulates that circuits supplying such equipment must be provided with a separate equipment grounding conductor. This means that the dryer's metal frame or chassis needs to be connected to ground via a dedicated grounding wire, independent of the neutral conductor. Because the circuit is no longer fed directly from the service equipment, the exception that might have allowed the 3-wire connection no longer applies. Therefore, simply replacing the cord and receptacle and continuing to bond the dryer to the grounded conductor is not compliant with current electrical code. The proper and safest solution is to run a new 4-wire branch circuit to the dryer location. This 4-wire circuit will include 2 hot wires, a neutral wire, and a dedicated equipment grounding wire. The equipment grounding wire will provide a low impedance path for fault current to return to the source, tripping the circuit breaker and minimizing the risk of electrical shock. To perform this upgrade correctly, firstly disconnect the existing 3-wire circuit at the subpanel. Turn off the breaker that supplies the circuit and verify that the power is off using a voltage tester. Secondly, run a new 4-wire cable from the subpanel to the dryer receptacle location. The cable should be sized appropriately for the dryer's amperage rating, consulting NEC Table 310.16 for proper ampacity based on the wire gauge and insulation type. Thirdly, install a new 4-wire receptacle at the dryer location. These receptacles have 4 slots, one for each of the 2 hot wires, one for the neutral wire, and one for the equipment grounding wire. Fourthly, connect the wires in the subpanel. Connect the 2 hot wires to the breaker, the neutral wire to the neutral bus, and the equipment grounding wire to the grounding bus. Ensure all connections are secure and properly tightened. Fifthly, connect the wires to the new 4-wire receptacle. Connect the 2 hot wires to the appropriate terminals, the neutral wire to the neutral terminal, and the equipment grounding wire to the grounding terminal. Again, ensure all connections are secure. Sixthly, at the dryer itself, disconnect the existing 3-wire cord. You will need to purchase a new 4-wire dryer cord. Seventhly, connect the new 4-wire dryer cord to the dryer's terminals. Connect the 2 hot wires, the neutral wire, and the equipment grounding wire according to the dryer manufacturer's instructions. Most dryers have a bonding jumper that connects the neutral terminal to the dryer chassis. This jumper must be removed when using a 4-wire connection. Eighthly, after completing all the wiring, double-check all connections to ensure they are secure and properly tightened. Verify that the equipment grounding wire is properly connected to both the subpanel grounding bus and the dryer chassis. Ninthly, turn on the breaker at the subpanel and test the new receptacle using a receptacle tester to ensure it is wired correctly. The tester should indicate that the wiring is correct with proper grounding. Finally, if everything checks out, you can now safely connect the dryer to the new receptacle. This 4-wire connection provides a much safer grounding system, minimizing the risk of electrical shock in the event of a ground fault. It is crucial to adhere to the NEC guidelines and local electrical codes when performing any electrical work. When in doubt, it's always best to consult with a qualified electrician to ensure the work is done safely and correctly. Remember that electrical work can be dangerous, and it's important to take all necessary precautions to protect yourself and others. Always work with the power off, use appropriate safety equipment, and follow all applicable codes and regulations. Ignoring these requirements and continuing to use a 3-wire connection for a dryer supplied by a subpanel is a safety hazard and a violation of the NEC. By upgrading to a 4-wire circuit, you are ensuring the safety of yourself, your family, and your property. The NEC is not just a set of rules, it is a guide to ensuring electrical safety. It is regularly updated to incorporate new technologies and address emerging safety concerns. Staying informed about the latest code requirements is essential for anyone working with electricity. When dealing with electrical systems, it is crucial to prioritize safety above all else. Shortcuts or compromises can have serious consequences. By following the NEC and best practices, you can help prevent electrical accidents and ensure the safe operation of electrical equipment. The requirements outlined in the NEC are based on years of experience and research. They are designed to protect people and property from the hazards of electricity. Understanding and adhering to these requirements is essential for anyone involved in the design, installation, or maintenance of electrical systems. In addition to the specific requirements for dryer circuits, the NEC also contains general requirements for grounding and bonding that apply to all electrical systems. These requirements are designed to create a low impedance path for fault current to return to the source, tripping the circuit breaker and minimizing the risk of electrical shock. Grounding and bonding are essential for electrical safety. They provide a path for fault current to flow back to the source, allowing the circuit breaker to trip and de-energize the circuit. This helps prevent electrical shock and fire hazards. The equipment grounding conductor is a critical component of the grounding system. It provides a direct connection between the metal parts of electrical equipment and the grounding system. This ensures that any fault current will flow back to the source, tripping the circuit breaker and de-energizing the equipment. The neutral conductor also plays a role in the grounding system. It provides a return path for normal current flow and also helps to carry fault current back to the source. However, it is important to note that the neutral conductor is not a substitute for the equipment grounding conductor. The equipment grounding conductor must be a separate wire that is dedicated to carrying fault current. Bonding is the process of connecting together all of the metal parts of an electrical system. This creates a common ground potential, which helps to prevent electrical shock. Bonding is typically accomplished by using bonding jumpers, which are short lengths of wire that connect together different metal parts. The NEC specifies the size and type of bonding jumpers that are required for different applications. In addition to the requirements for grounding and bonding, the NEC also contains requirements for overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from damage due to excessive current flow. These devices are designed to trip or blow when the current exceeds a certain level, interrupting the flow of current and preventing damage to the circuit. The NEC specifies the size and type of overcurrent protection devices that are required for different applications. It is important to select the correct overcurrent protection device for each circuit to ensure that it is properly protected. In addition to the technical requirements, the NEC also contains requirements for workmanship. These requirements are designed to ensure that electrical work is performed in a safe and professional manner. The NEC specifies that all electrical work must be performed by qualified individuals who are trained and experienced in electrical work. It also specifies that all electrical work must be inspected and approved by a qualified electrical inspector. Following the NEC and best practices is essential for electrical safety. By taking the time to understand and adhere to these requirements, you can help prevent electrical accidents and ensure the safe operation of electrical equipment. When working with electricity, it is always best to err on the side of caution. If you are not sure how to do something safely, consult with a qualified electrician. Electricity is a powerful force, and it should be treated with respect.